Hello everyone. This talk is on high-performance edge inference with RedisAI. I am Masoud Koleini, a solutions engineer at Arm. For this talk, we go through challenges and benefits in IoT world, lightweight inference on edge, benchmarking RedisAI, talk about RedisAI best practices and a case study which we orchestrate using K3s Kubernetes platform, then show you a demo and talk about Arm's project Koleini. I joined Arm as a research software engineer and worked on edge computing, stream processing, and machine learning pipelines. Now I work with partners on benchmarking and optimization of their products on our machines. There are challenges and benefits in IoT world. Data analytics on the edge for applications like image processing, anomaly detection, and log analytics are getting more attraction from industry, with an expected growth of about 15% per year in the next several years. There are several challenges in this area. First, edge devices have limited resources like memory and CPU. Their connection to the cloud is not reliable, and not so many applications are written with the focus to run on small devices. However, edge analytics benefits are they offload computations from cloud to thousands of edge devices that may have available resources, reduces latency by keeping the analytics engine close to the data store, and in the absence of reliable connection to the cloud, provides robust performance by allowing the edge devices to make decisions on themselves in critical conditions. This is a case study on lightweight inference on the edge. We benchmark RedisAI CPU GPU inference rate and memory usage on NVIDIA Jetson Nano that we are using as an edge device. Provide technical information and best practices for running RedisAI applications on our machines. Deploy a case study application using K3s Kubernetes and demo the application. RedisAI is a Redis module specifically written for running deep learning inferences on the data stored in Redis. Redis supports tensor data format. RedisAI can connect to multiple machine learning backends such as Tensorflow, TensorFlow Lite, PyTorch, and ONNX. The ML inference it provides to the users is extremely simple to work with. Users can load models, create tensors inside Redis, then run models on the tensors, and read the results back. RedisAI has APIs available in popular languages like Python and Go. For the benchmarking, we are using NVIDIA Jetson Nano. It is well suited for low-power AI IoT applications. With 128-core Maxwell GPU, quad-core Arm Cortex A57, and choice of 2 GB or 4 GB of memory. For benchmarking, we use AI Bench, a benchmarking tool for RedisAI. Here on this slide, there is a link to the repository for everyone that would be interested in reading the code and to find out how to run the benchmarks. It uses MobileNet v1 for image classification for TensorFlow and TensorFlow Lite backends. We use these two backends, TensorFlow and TensorFlow Lite, to compare their inference rate and memory usage. TensorFlow Lite models are serialized as flat buffers, which are memory and speed optimized. In addition, it is possible to use quantized models with smaller sizes and faster performance, but somehow lower accuracy. For GPU-accelerated inference, you can only use floating point or non-quantized models. Here on the slide, there is a link to hosted TensorFlow Lite models for mobile and IoT devices. You can also compare model size, performance, and accuracy for different versions, and also compare those parameters for quantized and floating point models. Here is a result of inference rate benchmarking for MobileNet v1 on TensorFlow and TensorFlow Lite backends. The left chart is the CPU inference rate, and the right is the inference rate for the GPU acceleration. The orange line shows TensorFlow inference, and the blue line is for TensorFlow Lite. The x-axis is the tensor batch size. It is clear from the charts that TensorFlow Lite performs better when the batch size increases. We have similar results for memory usage. TensorFlow Lite uses a lot less memory compared to TensorFlow for the same model and for both CPU and GPU inferences. The benchmarks demonstrate that TensorFlow Lite would be a convenient choice for running on resource-constrained devices. At the time of this talk, TensorFlow Lite GPU inference is a work in progress. However, you're still able to use it with some restrictions. To do so, please go to the RedisAI repository and you can find a pull request for TensorFlow Lite GPU Inference, and your contributions and bug fixes are welcome. A couple of results from the benchmarks. TensorFlow Lite models can run more efficiently on small devices, and RedisAI supports TensorFlow Lite CPU and GPU inference. However, we can't always use TensorFlow Lite since not every TensorFlow model is convertible to TensorFlow Lite. The reasons are TensorFlow Lite operations are limited compared to TensorFlow, and the same holds for data types. In addition, quantization may reduce the accuracy of the inference, and therefore it may not be suitable for some applications. To enhance the performance in practical scenarios, there are several best practices to follow. First is to use RedisAI pipelines. It allows clients to batch multiple commands in a single request instead of sending each command separately. That reduces the delays incurred by network latency. RedisAI offers a feature called auto-batching. In the presence of multiple clients sending data for inference, RedisAI can batch all the requests into a single tensor batch and run inference one single inference per client. You can think of clients as cameras sending images to RedisAI for image classification, and RedisAI creates a single tensor batch from all the images and runs inference on the batch. That again improves the performance. The other feature to increase the performance is DAG execution. DAG execution specifies a directed acyclic graph of operations to run on RedisAI. The performance enhancements that DAG provides is that tensors are created in the local memory and don't get stored into Redis database. That again saves some operations and increases speed. Edge computing devices usually collect data from sensors and peripherals as streams. Redis has data structure called Redis streams. It stores the streaming data into Redis in an append-only format. To run inference on a stream of data, we need a component that can glue Redis streams and RedisAI together. Redis Gears is a module specifically designed to implement data flows and pipelines in a programmatic way. Users can write process pipelines in a language like Python, and Redis Gears will execute that on the data stored in Redis. Like data streams, running the pipeline close to the data source reduces the latency and increases the performance. In the right-hand side, you can see an image showing how it works. It has its own components, its pipeline, it reads data from Redis store, and pipeline gets triggered by events. To understand more about how RedisAI, Redis streams, and Redis Gears work, you can look at the many well-written documentations on Redis website. For this case study, we demonstrate an animal recognition system. It uses MobileNet v2 to classify images and detect images that have cats in them. The images come from a camera that is connected to the system. Jetson Nano devices have 1 or 2 CSI slots for camera connection. It is also possible to use USB cameras to connect to the device. The system has multiple components. Redis server with RedisAI and Redis Gear modules loaded, an initialization script that loads the model into RedisAI, then initializes 2 streams of images. One stream for the images that are received from the camera, and another stream from the images that are detected as cat images. There are 2 front-end HTTP servers. One server reads from the streams with all the images and shows them to the user. The other stream reads from the stream with cat images. To understand how this case study works, which could be a good practical example for you as well, you can refer to the link on the slide that points to the repository. You can look at the codes for all the elements in the system and run the case study on your machine. The demo we show for you in this talk is a bit different from the way we orchestrate the containers on the repository. We use Kubernetes for deploying the application here, and specifically we use K3s, a lightweight distribution of Kubernetes to run on Jetson Nano. You may be familiar with daemon sets in Kubernetes context. They run a copy of pod on all the nodes that share a specific property. For example, they use a specific label or have the same architecture. That is important for IoT applications, where we may have thousands of nodes of the same type running the same application. In that case, using daemon sets allows us to deploy an application on all the nodes at once, update the application, or destroy them. Therefore, daemon sets would be a good candidate for managing IoT applications through Kubernetes. Now this is how the application works. Camera container reads from an actual camera that is connected to a CSI slot and stores the images that it reads into Redis server in the stream that holds all the images. Redis Gears pipeline is registered with the input stream, and images entered the stream triggers a pipeline. Pipeline reads the new images, run inference on it, and if a cat is detected in the image, it adds the image to the output stream. One front end reads the image from the input stream with all the images and shows that to the user, and the other one reads the output stream with the cat images. This scenario simulates a realistic application. On Jetson Nano, K3s is configured to connect to Docker, which uses NVIDIA Container Runtime to create containers. This is specifically important if you would like to use GPU acceleration from inside containers in your machine. And note that for this case study, we are using CPU inference, by the way. The system consists of 5 containers: one init container, one Redis server, 2 front-end containers for all images and cat images, and a camera container that reads images from a camera connected to CSI port on the device. To spin up the system, K3s agent on the node gets pod specification from K3s server running on the cloud. In Kubernetes context, containers run inside the pod, which is created as Kubernetes daemon set. We talked about Kubernetes orchestration in previous slide. Kubernetes is a well-known container orchestration platform. Native Kubernetes is a bit heavy to run on resource-constrained devices. We use K3s in our case study, which is developed by Rancher and is a lightweight distribution of Kubernetes that is optimized to run on Arm machines. The installation, configuration, and uninstallation of K3s is very simple, and you can find more about it if you go through the link on the slide. Now here is a demo for animal recognition system running on NVIDIA Jetson Nano. You can find all the materials to replicate this demo on your own in a blog post with the same title on Arm community website. I will give you the address of the blog at the end of this presentation. For this demo, we are assuming that all the Docker images are created. You can see that we have Docker images for camera, initialization application, front-end, and Redis. In addition, container runtime should be set to NVIDIA runtime. You can see that from etc docker daemon.json. And here, the default runtime is NVIDIA. You should have K3s installed on your edge machine with Docker support and connected to master. You can see that we have arm-jetson ready, which is our Jetson Nano node, and now we can deploy application on it. Now let's look at the YAML configuration for the application. It is a daemon set that will run on all the nodes that are labeled with device at Jetson Nano. It has Redis container, weball front end which reads all the images, webcast front end that shows all the cat images, camera container that can read from a USB camera or a camera that is connected to CSI port. We are running initialization script as a job, as a Kubernetes job, which runs once, initializes Redis, and terminates. It runs on the same nodes with the same label. The next step is to deploy the application. We can see that daemon set and job are created. Let's look at the pods. The animal pod, which contains the 4 containers of the application, is running, and the initialization app is completed. That means that it has successfully initialized the Redis. Let's look at the front ends and see how they work. If you are interested to learn more about RedisAI, you can read more about it and specifically its real-world industrial applications on Arm Project Koleini website in High-Performance Edge Inference Blueprint. In addition to try the demo yourself, learn about best practices, find example codes and Docker files, we have a blog post with the same title as this talk on Arm community website with the address on the slide. The other helpful resource is the animal recognition demo repository itself that I mentioned before. There we have all the Docker files that you need to run demo on Jetson Nano. I talked about Project Koleini in previous slide. Project Koleini is a collaborative initiative covering standards, platform security, and reference implementations with cloud-native standards at edge. That helps users to deploy their applications on the edge and connect them to the cloud in a secure manner. We have many partners joining Project Cassini ecosystem. That allows users to run their applications on different platforms without experiencing any difficulties. Redis and RedisAI are such examples. They can run inside containers on Arm machines. Therefore, they can benefit from cloud-native software stack for orchestration and management. Cloud-native experience helps edge analytics applications to run on thousands of devices seamlessly. You can find lots of information about Project Cassini on its website with the address on the slide. Thanks for listening to this talk, and I would like to thank Redis Labs and Orbix team for helping me through this case study.